Okay, welcome back. So I promised to say a little bit about course expectations and that kind of thing. There'll be some similarities, but also some differences from the fall. So there'll be so in the fall we had exercise sets and problem sets, and that was it. So no problem sets. Probably many of you will not miss them, but so no problem sets. Those were the hard ones. Instead, there's going to be, so the focus of this class, sort of today notwithstanding, the focus of this class is on recent research, like I said, the last 5 years mostly. And so it's a good opportunity to do a research project. So maybe around the 4th week of the class or something like that, I'll post a list of various research papers that I think might be fun to read in more depth. And so the deliverable will be some kind of research report, say ballpark 15 pages, something like that. If you want, you can just do sort of a paper summary, paper synthesis. But for those of you that are looking for kind of research problems to work on, this is another natural opportunity to spend some time on that. Exercise sets, there will be some, including starting this week. Exercise set number 1. There's a very, very bare bones web page at the moment, but exercise number 1 is linked to from the web page. And those have the same format as last quarter, meeting only once a week. I actually think they're sort of probably even more crucial for the first part of the class, just to keep you engaged with the material and just to keep you sort of, to get you solid on all these concepts. I'm probably going to have them tail off once we get to the midpoint of the quarter, and where I'm expecting you to spend more time on the research projects. So expect kind of maybe 4 or 5 exercise sets of a similar length to the fall, and then maybe, ones that have, say, 2 to 4 exercises for the second half of the class, something like that. Yep.
Do we turn in the exercise sets, or are they just for our practice?
You turn them in.
Okay.
Yeah. And if you look at the PDF on the, I'm not going to bring hard copies, but the PDF has full instructions about, exactly, what the honor, what resources you can use and working with other people and so on. Those of you who took it in the fall, it's the same policies as in the fall. And right, and so then also, like last quarter, we are videotaping the lectures. That said, I am thinking of attendance as roughly required. We're a small enough group. It would be sort of a shame if half of you didn't come just to watch it on YouTube later. I know some of you are going to have interviews and stuff, and I realize there'll be conflicts, but barring kind of hard conflicts, I do actually expect you to attend the lectures and use the videos for review or for the few lectures that you absolutely have to miss. And there will be lecture notes, just like last quarter. Also, just like last quarter, I'm not really going to promise a bound on the latency of the lecture notes. Sometimes they'll be fast. If I have a lot of other deadlines, they may not be so fast. So I'll do my best, but I'll get them out when I can. And the website, as usual, will have sort of related readings to the lectures. I'll get that up probably tomorrow. Questions? Yeah.
2 questions. If we were taking this class per credit,
Yeah.
is there any difference?
Pass-fail, you mean?
Yeah.
Yeah, you do not have to do the research project if you're taking a pass-fail.
And how would you compare this in terms of workload to the predecessor to 364A?
It's hard for me to say. I'm nervous of saying anything on the record about that because there's a little apples and oranges, with the research project, which to a large extent, I hope some of you will feel motivated to work extremely hard on the research project. But and on the one hand, there are these brutal problem sets in 364A, but there are also, groups of size 3 that you could work on them together. So that makes it a little hard for me to do the arithmetic. As far as what I'm shooting for it to be a little less time consuming overall. Feel free to let me know in the evals if I succeed or not at the end of the quarter. But last quarter I imagine was pretty time consuming. And this quarter I mean to be rigorous, but not quite as time consuming. But we'll see. Your mileage may vary. So, other questions? All right. So hopefully now it's sort of clear what the plan is. Okay. So we want to look at more interesting, more complex scenarios. Okay, of allocating scarce goods to people in a way that gets good performance. In this case, good surplus. And ultimately, our focus is on having ascending auctions, which are ex post incentive compatible, since your bidding leads to good performance and are simpler polynomial time. And I left you last lecture with the observation that a prerequisite is you need to at least have good direct revelation dominant strategy mechanisms before you could hope to have this. So that's the paradigm I want to start exploring for scenario number 3, a more complex scenario in this lecture now. Okay. So scenario 3 is going to be a strict generalization of scenario 1, and it's still going to be incomparable to the additive valuation, scenario number 2. So we're going to have, like scenario number 2, we're going to have non-identical items. And like scenario 1, we're going to have unit demand bidders or valuations. By which I mean bidder I has a private value Vij for good j, and we define bidder I's value for a bundle of goods S. So in the additive case, it was the sum over the goods in the bundle. Here it's going to be the max over the goods in the bundle. Okay. So again, unit demand means you're not interested in more than one item, but you do have preferences amongst them. Houses, for example, is often used as an application here, right? So you're not going to buy more than one house potentially, but there are some that you would be willing to pay for more than others. Okay? So the goal, which is actually going to take all of this lecture and a little bit at the beginning of next lecture as well, next week. But the following goal is to construct an auction with all of these properties for scenario 3. Okay, that turns out to be a really interesting problem. Okay, the solution is really nice, but we have to develop a reasonably deep understanding of the scenario to justify the eventual solution. Okay? So, as we said, the sanity check, just to even wonder if this exists for unit demand bidders and different items, well, do we at least have a direct revelation DSIC implementation for scenario number 3? And we do. So first, I think I put this on an exercise in the fall, but I want to point out that there's a very strong connection between seeking to maximize surplus with unit demand bidders, unit demand valuations, and bipartite matching. Okay? So suppose we just wanted an algorithm to maximize surplus. So if you want, think of this as the allocation rule in a VCG mechanism. So suppose you actually knew all the Vij's, and you just wanted to compute a surplus maximizing valuation. Okay. Well, because bidders are unit demand, it's pointless to give a good or more than one good. Okay? If you gave it 2 goods, it's just going to throw out the one that it likes less anyways. Okay, so without loss, each bidder gets at most 1 good. So to max surplus, without loss of generality, at most 1 good per person. And of course, each good only goes to 1 person. You can't give a good to 2 different people. Okay, so we can think of this as a bipartite graph with bidders on one side and goods on the other side. And the edge weight is just equal to the valuation that a given bidder I has for the given good J. Okay? Maximizing surplus is just maximizing the Vij's over all pairs Ij where bidder I gets good J. So that just corresponds to computing a max weight bipartite matching in this graph. So corollary, maximizing surplus, ignoring incentive issues. Maximizing surplus with these unit demand valuations is equivalent to max weight bipartite matching. So something I hope many of you have seen at some point in your education is a polynomial time algorithm for max weight bipartite matching. You can solve it using linear programming. There are lots of combinatorial algorithms for it as well. In fact, next week we're going to see, possibly one of the simplest algorithms known that computes a max weight bipartite matching. Okay, up to an epsilon. But it'll still be a very simple algorithm that shows that this is a computationally tractable problem. It's not trivial. Okay, I don't teach it in my undergrad algorithms class, for example, but this can be solved quickly. All right, so what? Okay, what about incentives? Well, something that I hope you might maybe remember from last quarter is that the surplus objective, if you want to maximize it with a DSIG mechanism, is a very special objective. We basically have a universal solution for doing surplus maximization in a dominant strategy way, and that's called the VCG mechanism. And so again, what I'm doing here is I'm doing a direct revelation D6 solution to this problem as a sanity check before we move to the ascending implementation, which is the hard part. Okay, so what is the VCG mechanism? Let me jog your memory. I guess I should say, so the VCG mechanism is defined super generally. Okay, this is just a very powerful tool if you only care about dominant strategy implementations and surplus maximization. Kind of always gets you those two properties. Very often it's computationally intractable, but one thing that's special about scenario 3 is that it's not going to be computationally intractable. It's going to be polynomial time implementable because surplus maximization is just a matching problem. Okay? So it's direct revelation, so you just ask people for their private information. So you collect the BIJs. Now you're thinking of these as being truthful and you want a surplus maximizing outcome, so it's clear what your allocation rule should be. You just take the bids at face value, assume they're the valuations, and compute the thing with the maximum surplus. That is, the second step is you compute a max weight bipartite matching with the bids being the weights. So here's the allocation rule. So you compute the max weight matching with respect to the bids. And then you charge the right prices, okay? And I'm going to be a little informal about the VCG prices right now. Okay, we did go through them in detail last quarter. I'll remind you about the actual formula a little later. But the gist is you charge people their externality, okay? So charge each bidder its externality. What do I mean its externality? I mean, like, well, first, imagine that this bidder I didn't exist, and we only optimized for the other n-1 bidders. We get some number. Now, suppose instead we optimize jointly for all n bidders, and we just look at how much of that surplus the other n-1 bidders get. Okay, that's an only lower number. Okay, they're going to get more surplus if I optimize specially for them. Okay, so the difference of these is a non-negative number, and that's the payment under the VCG mechanism of this bidder. Why do you charge people their externalities? The externality can also be thought of as the difference between the social objective function of surplus and the individual objective function of just what you get minus your payment. And we proved last quarter, it was a simple proof, that these payments align those objectives, and therefore, indeed, truthful revelation is a dominant strategy with these payments. Okay? So that's, I just wanted to remind you conceptually what these payments are. I'll give you the formula when we actually need the formula in a little bit. Okay. So this is good. So this means the sanity check passes. We want an ascending implementation. We asked, is there at least a polynomial time DSIC implementation? Yes. The reason, we can implement VCG in polynomial time in this particular case. Okay? So we passed the sanity check. Now, the hard part, or the interesting part perhaps. So I guess it's still here. Right, so the goal is just to get these three properties for scenario number 3. So high-level design plan. I should also mention, so this is scenario 1, that was identical goods and unit demand. That's the special case where these VIJs are independent of I. Okay, well, independent of J, where all bidders have the same VIJ for every good J. Sorry, each bidder I has the same VIJ for every J. It's incomparable to additive valuations because here it's unit demand, and that's just a different thing than additive. Okay, so we're generalizing scenario 1, we're incomparable to scenario 2, but somehow we'd still like to apply the same type of thinking when we design an ascending implementation. And the two auctions we've seen so far are based on you start prices at 0, things are over-demanded, people want lots of goods, but then you increase prices until supply equals demand. Okay, so that was true in the original English auction where you had a supply of K. It was true in the parallel English auctions where you had a supply of 1 for each of the M different goods. So it's going to be I'm not even going to tell you the final auction until next week, but at a high level, where we're going is we want to initialize P equals 0, and we want to raise prices for the various goods as needed till supply equals demand. Okay? All right, so what does this mean? Okay, I want to drill down on this. So this is like our 30,000-foot high-level idea of what this thing might look like. All right, so supply is clear. So we have one copy of each of the M items. Okay? What's demand?
You give me a vector of prices and say at these prices, which single item would I most prefer?
Good. So in the original English auction, where there was only one kind of good for sale and we were looking at a given price, we just asked people, do you want it or not? Okay, so every bidder contributed a 0 or 1. We added up how many people wanted it. We just compared it to K. Okay, so it was a yes/no question. Sort of the same thing with the parallel English auctions. For each English auction, it was a yes/no question. Do you want this or not? Okay. Now, with unit demand bidders here in different goods, at the end of the day, we know a bidder is only going to get one item at most. So we're actually not going to ask it a yes/no question. We're going to ask it a richer question. We're going to say, well, given the prices that we've currently set for each of the M items, which one's your favorite? Okay. What does favorite mean? Well, it means your net utility for it is the highest. Your value for it minus the price you'd have to pay. Okay. And so now a bidder, instead of just contributing, one number, it contributes in some sense one number to one of the goods, exactly one of the goods, or at most one of the goods. So rather than overall demand, let me just say demand of I, a bidder I, is going to be its fave good at the current prices Q. And again, by fave, I mean highest Vij minus Qj. And of course, if all of these are negative, then the bidder says, I don't want any of them at the current prices. Okay, so your demand can be the empty set as well. Okay. So with that notion of demand, we can start thinking about, does supply equal demand or not? So we look at a good. If it's more than one bidder's favorite, then it's over-demanded. Okay, if there's a good that nobody wants, then it's under-demanded. Okay? And so certainly if you're over-demanded, that suggests the price is too low. It suggests maybe you should raise the price. Okay? So again, the full description will have to wait till next week, but I wanted you to kind of have in mind what's the general form of the ascending auction going to look like. What are we shooting for? Okay, so this is sort of how we're thinking it's going to work at a high level. Good. Now, so another goal, in addition to having this kind of description, we want sincere bidding, by which I mean every time we ask a bidder for its favorite good, it tells us which one is its favorite with respect to its actual valuations. We want sincere bidding to terminate in the VCG outcome. Okay? Now, I've actually, if you're paying close attention, you notice actually I just made this a slightly stronger goal than it was before. Okay? So what I said our goal was to have an ascending auction, that's fine. Epic, that's fine. And I said I wanted sincere bidding to lead to maximum possible surplus. Okay? Now, an outcome of a mechanism like VCG is two things. It's an allocation, it's a payment. And it's certainly the case in the VCG outcome, the allocation is efficient. It's maximum surplus. And the payments are whatever there are. So I just strengthened our goal from wanting some outcome that has maximum surplus at some prices to actually wanting a maximum surplus outcome at the VCG prices. You might wonder why I did that. Turns out it's necessary, but I'm not going to tell you till a future lecture why it's necessary. You might say, well, why don't we have a surplus maximizing allocation at some possibly different prices? Turns out that approach is doomed to failure. Okay? If we want maximum surplus in an epic mechanism, it's going to have to be through the VCG outcome, including the VCG prices. Okay? So take it on faith for now that we're going to want this to be the goal. Okay? We want not just a surplus maximizing allocation, but we want the prices at termination of our auction to be those of the VCG mechanism, if we'd run it, which we're not, but if we'd run it. So we want to simulate the VCG outcome. Now, given that, here's the key challenge. Okay? So again, the challenge given that what we're doing is confining ourselves to these very simple price ascending, make supply equal demand mechanisms on the one hand, and secondly, that we want to mimic the VCG prices at the end of the day, is that this is not, these VCG prices, this is not such a trivial computation. Right? The VCG payment of a bidder is you charge it its externality, which is the difference of two different matching computations. Right? So basically you compute the matching for everybody, and then you compute the matching if I deleted, and you take the difference of these two numbers. And that's the definition of the VCG payments. Okay? So we know how to do it in polynomial time, but that's not some just like closed form formula or some easy thing to write down, these VCG payments. Whereas these ascending auctions, just these sort of simple ascending price raising things, it doesn't feel like they're doing very complicated computations. So it feels a little ambitious maybe to use this kind of very simple computational model, if you will, of these ascending auctions to compute something as intricate as these VCG payments, these differences of matchings. Okay? That's why this seems, at worst, hopeless or false, and at best, a little tricky to prove. Okay? Turns out it's merely a little tricky to prove. Okay? So key challenge, how to ensure prices at termination, again, computed with these simple ascending procedures, actually equal the seemingly rather complex VCG payments. Okay? So here's the proof plan. Okay, but just to be clear, we will succeed in this. We will accomplish this. So today, what we're going to do is we're just going to focus on the VCG payments, and we're going to understand that they're rather simpler than they at first appear. Okay? So we're going to characterize the VCG payments in a way that are much more understandable and much more plausible as the output of an ascending auction. Next week, I'll finish the construction and actually prove to you that an ascending auction can compute those prices. Okay? So today, characterize VCG prices as, so this is not going to make sense. This is, again, just to kind of give you a forward pointer. But we will do this today. I'm going to introduce the notion of Walrasian equilibria, which is the appropriate notion of market clearing prices for these matching settings. And we're going to show that there's, in some sense, a smallest. There's not one Walrasian equilibrium. There can be many. But in some sense, there's a smallest one. And we're going to prove that the VCG payments are exactly the smallest Walrasian equilibrium. And this will be interesting because Walrasian equilibria are much more plausible outputs of ascending procedures than this difference of matchings. Okay? And then next week. So next week, auctions such that sincere bidding. We're not going to prove directly that it converges to the VCG payments. Rather, we're going to prove that it converges to the smallest Walrasian equilibria, which by our labors today we'll know actually are the VCG prices. Okay? So it's sort of the forest clears, the big picture clear. Okay. So the end goal is an ascending implementation for these unit demand heterogeneous goods. That's going to require simulating the VCG outcome. And the topic for today is to understand the VCG prices in the simpler way as Walrasian equilibria. Okay? All right. So the rest of today, we do this. All right. So, what is a Walrasian equilibrium? So this definition, you can make this definition very general. I'm just going to give you the suitable notion for scenario 3, for unit demand bidders. Okay, so here's how you define it for scenario 3. So you also hear these called competitive equilibria sometimes. So I'm going to abbreviate it WE. So it's a pair. So it's a price vector, Q, so a price for each of the M goods, and an allocation. Again, we can think of allocations as matchings without loss of generality. M, so that the following conditions hold. The main condition is that everybody should be getting their favorite good at the current prices. Okay? So each bidder, I, matched to its favorite good. So I'm going to use, for a bidder I and a matching capital M, I'm going to use M of I to denote the good J that I gets. It's possible that I gets no good. Then I define this as the empty set. And the value of an empty set is 0, and the price of an empty set is 0. Okay? So in general, we could have more bidders than goods. We could have more goods than bidders. Everything I say will be relevant either way. So we have a bidder I. It's matched to some MI. And MI should be its favorite, meaning it's an argmax, favorite in the same sense that we mentioned when we were defining demand. Okay? So argmax over J, Vij. Let me switch the notation a little bit. Vij minus Qj. Okay?
Well, we're including this empty set, 0.
We are. Let me actually, but so let me just, let me be redundant and write a little extra. Or none, or no good. So in other words, MI should be empty if all these values are negative. Okay? So in particular, every bidder should have non-negative utility. Okay? That's what this ensures. By itself, condition 1 is not interesting. Do you see why? There's some very stupid examples of Q's and M's that satisfy condition 1.
Set Q to be huge and give everyone nothing.
Right. So if you think of the Q's as plus infinity, then nobody wants anything, and you just set M to be the empty matching. Okay, so that certainly we wouldn't want to call market clearing. So the other condition is that a good J should go unsold only if its price is as low as possible, so 0. Okay, and by unsold, I mean in M. Okay, so I mean J does not arise as M of I for any bidder I. That's what I mean by unsold. Okay. Okay. So it's a new definition. We should get a feeling for it. So let me tell you interpretation, why we might care, some examples. So as far as interpretation, actually these Walrasian equilibria, if you think about it, these are kind of magical. Okay. So forget about M for a second. So just think about Q, right? So suppose you slap, just the Q part of Walrasian equilibrium, I'll call it, a price vector, Walrasian equilibrium price vector. So suppose you just have one of those Qs and you slap them down on the goods, okay? And now all the bidders just sort of walk up and they see these price tags on the goods, these Q of J's, right? And without coordinating at all, then they're like on a shelf, okay, with the price tags. And every bidder just walks up and chooses the one that they like the most, okay? With no bearing to the other people, okay? So everybody individually optimizes their own utility according to the announced prices, the price tags Q. Well, then you get so assuming there's no ties, you're going to get back this matching M. Okay, so in particular, nobody's going to choose the same good. There's going to be no conflicts, despite the fact that everybody made independent decisions. Okay, so these Qs, this is the sense of market clearing of these Walrasian equilibria. You announce the prices, you let people do whatever they want. There's no conflicts, no good is over demanded. The only goods left on the shelf are those that were priced 0 anyways, so nobody wants them. Okay? So that's sort of how we often think about Walrasian equilibria. They're prices that just decouple individuals' optimization problems. They can just solve them separately and there's no conflicts and the market clears. So that's pretty cool. Why am I talking about these? Why might they have anything to do with, say, ascending auctions? Well, recall sort of our high-level design plan. We're adjusting these prices until supply equals demand, okay? And so what are demands? Demands are favorite goods. Supply equals demands means, essentially all goods should be demanded one. Okay? So we're envisioning this auction terminating with prices that seems like they should look like a Laplacian equilibrium. Right? So everybody picks their favorite good. No good is over demanded. You're only under demanded if the price was zero anyways. So looking ahead, the reason we're talking about these is because if we run this high-level idea of an ascending auction that we have with supply equal demand to completion, completing with these market clearing prices, that's going to be a Laplacian equilibrium. Okay, so these objects are the natural termination point of the family of ascending auctions that we vaguely have in mind right now. Okay, so that's why we're going to talk about them. I mean, obviously, this is, this also says why it's a good reason to talk about them, because they let us understand VCG payments. But there's an even more intuitive connection. Okay, so some examples. So let's look at a single item auction. So this means we have one good. Maybe we have like four bidders, say. And let's say the values of the bidders for this good are 10, 8, 7, and 4. So what are the prices that arise in Laplacian equilibria in this example?
The interval 8 to 10.
Yeah. Everyone agree? So it's not unique. If you slap any price down on this item between 8 and 10, the three people with the lowest valuation are not going to want it, and the one with the highest valuation is going to want it. Okay? So if everybody walks up, this guy's going to take it off the shelf. The market clears, all the goods are sold, and these three bidders also have, they can't get non-negative utility from any of the goods, so they're also happy having nothing. Okay? So, again, just sort of foreshadowing things to come. What would be the price computed by the Vickrey auction or an ascending auction in this single item setup?
8.
It would be 8, right? Yeah, or 8 plus epsilon for the English auction. So essentially, just empirically in this example, the Vickrey or English auction is computing as its final price the smallest of the Laplacian equilibria of this example. Unclear what that means right now, but as we'll see, that's a general phenomenon. If you try to charge people the highest Laplacian equilibrium price, 10, that would be like a first price auction, right? And that we know is not dominant strategy incentive compatible. That does not have good incentive compatibility properties. So at least for the single item auction, we're observing a correspondence between the smallest, the lowest Laplacian equilibrium, and the prices computed by incentive compatible auctions. Okay, so just remember that. So let's look at another example. Because things can get a little more complicated. So let's say there's 2 bidders and 3 goods. Let's say the goods outnumber the bidders. And let's say the values are as follows. So for edges that are not in the picture, think of the value as being 0. So I claim that 0, 1, 0 is the equilibrium, is a Laplacian equilibrium price vector. Okay. So for that to be true, we would have to pair these red numbers, this price vector, with a matching, so that the pair of the matching and the price vector satisfied these conditions. So how many matchings in this graph could I choose with this price vector that would result in a Laplacian equilibrium?
At least 2.
At least 2. Okay, I have a lower bound.
3.
I have a conjectured stronger lower bound. How many people say 3? How many people say 2? Okay, well, so hopefully the 2 that are here are sort of uncontroversial. So that and that is going to be a matching, which makes things wise in equilibrium. So basically, this bidder shows up. So the issue, of course, as I'm sure you've all noticed, is there are ties, right? So it's not well defined to say a bidder picks its unique favorite good. Okay, they have to choose amongst them somehow. So one situation is where both bidders choose the lower of their 2 favorite goods. Another situation is where they both choose the upper of their favorite goods. Okay, those are both auras in equilibria. What's the surplus of those 2 matchings?
No, the surplus is 4.
Surplus is 4. Yeah, surplus is 4. Right? 3 plus 1 or 2 plus 2, which is also the biggest surplus of any matching in the example. So perhaps the controversial matching is this one, where the first bidder picks its top good and the second bidder picks its bottom good. So is that auras in equilibrium? Why not? It fails condition 2. Right? So in all 3 of those matchings, a good is left unsold. It was kosher if the top good was unsold, because that had price 0. It was kosher if the bottom good was left unsold. It has price 0, but it's not okay if the middle good is left unsold, okay? Because that has price 1. What's the surplus of that matching that doesn't work? 3. So that was not a max surplus matching. Okay. So I lied a little bit. You know, when I said the magic of auras in equilibrium is people just show up and with no coordination pick their favorite good off the shelf. When you have ties, you do need coordination to break the ties. Okay? If there's no ties, what I said is correct, because everybody has a unique favorite good. But with ties, you do need this kind of coordination. Okay. All right. Questions? Yeah.
What exactly is the smallest?
Yeah, it's not defined yet. Yeah. Hey, initially, auras in equilibrium weren't defined. So we'll get there. All right. Yeah.
If you always prefer to pick non-zero items among your ties, is that enough coordination?
Well, so, okay, so
You both pick the same.
yeah. So it's actually the bigger issue. I should have actually been clearer, which is the bigger problem is just over-demanded, right? So the bigger problem is where the top bidder picks bottom and the bottom player picks up, right? So there's like with the story where people just don't coordinate and do whatever they want, you also get this non-matching where this bidder picks this good and this bidder also picks this good. So you, at the very least, need coordination to just prevent people from choosing the same good more than once. The 0 problem maybe you can fix in some other way. But coordination with ties is fundamental to auras in equilibrium. Yeah.
Is it known when VCG is unique?
Yeah, so that's related to this point. Yeah, so I'm going to address that at some point. So the VCG, you mean the payments? They are unique. We didn't prove that in the fall. We only proved it for single parameter problems. But I don't want to do it today, but we'll do it later. Yeah. Okay. All right, so what I want to prove next is that it wasn't an accident that the matchings that worked had max surplus and the matching that didn't work didn't have max surplus. Okay, not an accident, that's general. So this is going to be a version of the so-called first welfare theorem, again adapted for the current simple setting. So first welfare theorem, generally the interpretation here is that the outcome of markets are efficient. So it's something people obviously argue a lot about philosophically, but mathematically the statement here is very simple. Consider an arbitrary auras in equilibrium with these unit demand bidders. Then it must be the case that the matching M maximizes the surplus. Okay. Only max surplus matchings participate in auras in equilibrium. think about it, this sounds sort of like good news, right? Because at some point we're trying to drive toward a connection between VCG outcomes and Walrasian equilibria. So it should sort of warm our heart that at least Walrasian equilibria are fundamentally about max surplus outcomes, as are VCG outcomes. Okay. So proof. All right, so just some notation. So, fix any Walrasian equilibria, QM. Let capital Q denote the sum of the prices of all of the goods. Okay. So for all we know, M may or may not be max surplus, but something out there is max surplus. Call it M star. Okay. So by the Walrasian equilibrium condition, every bidder is just as happy getting whatever good it gets as M at the price as Q as it would be getting the good it gets in M star at the same price as Q. So by the Walrasian equilibrium condition, for all bidders I, so again remember, whoops, M of I denotes the good that bidder I gets in a given matching, if any. If that's the empty set, the value is defined as 0 and the price is defined as 0. So this is true. Okay, so that's just condition 1, the Walrasian equilibria. So sum these over all I. Okay. Well, when I sum these over all I just get all of the edges of the matching M once. Okay, so this summed over I is just the overall surplus of M. There's going to be some stuff with some Q's. Here, this, by the same reasoning, this is just going to be the surplus of the allocation M star. Minus some stuff with some Q's. Okay? So what's up with the Q's? And also, why is this hypothesis 2 of Walrasian equilibrium important? Right, so to be clear, we know this is false if I drop condition 2, right? By the example we had. Set all the Q's to be infinity, M to be the empty set. Okay, this is clearly false. Right, so we better use hypothesis 2. We used 1 here. So to see that, let's try to understand what this is. So suppose I sum over all the bidders I. Maybe think about the case, to see the subtlety, think about the case where there's like 10 bidders and 20 goods. Okay, where there's a lot more goods than bidders. So suppose I sum over the 10 bidders. Okay, they're allocated these 10 goods at most. And I look at the prices of the goods that they get in this matching. How does that compare to the sum of all of the prices?
It's equal thanks to condition 2.
It's equal thanks to condition 2. So what Q's are missing here? So we sum this over I. The Q's that are missing are the Q's for the goods that weren't sold. Right? They have price 0. Okay? So even though there's fewer terms when we sum this over I, the sum's exactly the same. Okay? So surplus of the matching M minus Q. And over here, we just have some Q's. We don't really care about them. Okay, so sum over I, Q, M star I. So rearranging, right, so the point is, this is certainly a most Q. Okay. So rearranging, surplus of M is at least surplus of M star. When we add capital Q to both sides, this becomes a non-negative term. So if we drop it, it becomes only less. So that gives us this. So we're done. Okay, so M star may have been optimal, but so is M. Okay. So that's the first welfare theorem. So later when we do ascending implementations that have this discretization error, we're going to want an approximate first welfare theorem, saying that if you're almost a Walrasian equilibrium, you're almost optimal matching. So that's one of the exercises on the exercise set. But the proof is exactly the same. All right, so good. So we're starting to get some clues that maybe there are some connections between VCG outcomes and Walrasian equilibria. So let me just, there's a very simple fact I'm going to need in the next theorem, which I call the mix and match lemma. The proof is not hard at all, so I'm going to put it on the exercise set. It basically says, well, look, so Walrasian equilibria are pairs. There's a price vector and there's a matching. And we know that these things aren't unique, right? So for example, in this, we know there can be various Qs. There can also be various matchings. Mix and match lemma just says, give me any two Walrasian equilibria. I can pair them up in the opposite directions. I get Walrasian equilibria. Okay, so I can take any price vector participating in any Walrasian equilibrium, any matching participating in any Walrasian equilibrium, and put them together. I get new ones. Okay. So mix and match lemma. If M1, Q1, and Q2 are Walrasian equilibria for particular valuations. So are M1, Q2 and MQ21. See exercises. Okay, but it's not hard, just a few lines. Okay. All right. So now I want to actually get down to business with relating VCG payments and Walrasian equilibria. Okay, let's really try to start getting at the heart of the matter. So this theorem is going to say, we're not yet going to argue that there's any equations involved, but at the very least, we're going to say that VCG prices are no bigger than any Walrasian equilibrium. Okay, they're bounded above by every Walrasian equilibrium. So fix any unit demand valuations. So let P of G be the VCG payment by the winner I of J. Okay? So just to be clear, right, so Walrasian equilibria, the prices are on goods. Okay? They're not on the bidders. If you think about VCG, VCG assigns payments to the bidders. Okay? But with matching, you can transfer between them. Right? So in the VCG mechanism, bidder I pays $10. Well, what do they pay it for? Oh, they paid it for good 17. Let's just call the price of good 17 $10. Okay? So that's all I'm saying here. So for a given good J in the VCG mechanism, look at how much was paid by the winner of J in the VCG outcome. Call that the price of good J. If good J was unsold by the VCG mechanism, we're going to define this to be 0. Okay? So the VCG outcome induces a price vector on the goods. So if Q is a Walrasian equilibrium price vector, then P of J is at most Q of J for all items J. Okay? That's what I'm going to prove next. Walrasian equilibrium price vector is bound above what the VCG payments could possibly be. Okay? Now, if I could prove also, not just this, but also that the VCG payments themselves, in fact, are a Walrasian equilibrium price vector, then there's a sense in which that's the lowest, smallest Walrasian equilibrium. And we will, in fact, prove that. Okay, that's where we're going. But for now, I just want to say VCG payments, they're not going to be bigger than a Walrasian equilibrium. Okay? Okay, so is it clear, theorem statement? All right. So, proof. The proof is actually going to have a similar flavor to the proof of the first welfare theorem. Similar kind of maneuvers. start it down here. Okay. So if a good is unsold, so for a good J that's unsold by the VCG outcome, there's nothing to prove. Okay, we could define P of that J to be 0, so it's clearly true. So we're only interested in goods J that are awarded to somebody in the VCG outcome. Consider such a good J, say it was won by bidder I. Okay. So now, this is the first time in the lecture where we really need to write down the formula for the VCG payments, right? Which is not surprising. I mean, look at what we're asserting, right? We're asserting an inequality with the VCG payments on the left-hand side. So let's figure out, what was this again? What was this externality thing? So recall, so P of J is just the VCG payment made by bidder I. So it's the externality of I, conceptually. So what does that really mean mathematically? Well, it means do the thought experiment. Okay, so we already know what VCG computes. It computes some matching M. It gives some surplus to the bidders other than I. Now suppose actually we just recomputed a matching from scratch, tailored to get these n-1 bidders the biggest surplus possible. Okay, that's going to be some bigger number. And the VCG payment is the difference. So it's going to be the difference between the surplus enjoyed by the other n-1 players when I specially compute a matching just for them, that's m minus I, minus their share of the surplus when I computed a matching optimizing everybody's surplus. Okay? So where m is the VCG allocation, that is the one maximizing surplus for everybody, and m minus I equals opt matching after deleting bidder I. Okay? Can everyone read this? So again, this is all I'm doing right now is recalling the definition of the VCG payment. That's all I've done. Okay? So again, you say, what surplus would they get if I optimize just for them? What share of the surplus do I get when I optimize for everybody? Okay. So again, now I'm going to use the same kind of maneuvers as in the first welfare theorem. So let Q, oh right. So consider a law as in equilibrium Q. And consider the sum of the prices, as before. So I want to prove these QJs are at least as big as these PJs. So here's where I need the mix and match lemma. Right, so my definition of a Walrasian equilibrium price vector is just that it participates in some Walrasian equilibrium. For the proof, I actually really want to pair this with the efficient matching computed by the VCG allocation M. Okay, so by the mix and match lemma, QM is a Walrasian equilibrium, meaning it satisfies these conditions 1 and 2. Okay. So again, P is the VCG computation, Q is your favorite Walrasian equilibrium, which I want to prove is at least as big. So I'm going to do the same maneuver. I'm going to say, as I did here, except I'm going to do it with respect to just the bidders other than I. So by virtue of this being a Walrasian equilibrium, everybody's getting their favorite good at the price is Q. So everybody's at least as happy getting their good in capital M as they would be in the good that they get in M minus I. M minus I was when I optimized surplus just for these bidders other than I. So we have V sub K, M of K minus Q is at least, so again, this is because MQ is the Wallace in equilibrium. And it's happier in this case than if it got the good it got in M minus I at the current prices. Okay? So I did exactly the same thing as I did here. The only difference is I threw out player I. And the other difference is instead of using the matching M star there, which was optimal for everybody, I'm using as a competitor the matching M minus 1 I here, which is optimized for bidders other than I. So again, summing. What do I get? So I'm going to sum this over all bidders, the n minus 1 bidders different than I. Okay? So I haven't done anything interesting here. I've just copied this down. What is this when I sum over all of the bidders? We just did this. What is this? If I sum over all the bidders, this is Q. Oh yeah, good. Right. So if I do it over all the bidders, including I, this is capital Q. Therefore, as you say, if I do this instead over all bidders other than I, it's capital Q minus what's missing, and what's missing is Q sub I. Okay, the VCG payment. Sorry, the Q sub J, right? Q sub J. Okay, so I is the bidder that's missing, and then the good that it gets is J. Right, so these are the prices on the items. Okay, so if I sum this over everybody I included, I would pick up all of the goods with non-zero price. That's what we did over there, so that'd be Q. If I delete I, it's deleting the good J, so it's deleting the price Q sub J. Okay, that's what happens when I sum that. And then, again, this I'm not going to care about. I'm only going to care that this is at most capital Q. So rearranging, and again, remember what it is we want. What are we trying to prove? We're trying to prove that the VCG payment, VCG price induced for good J lower bounds any Walrasian equilibrium price on J. So I want a lower bound on Q sub J. Okay. So I have this Q sub J. This is a minus Q. So if I add it to this side, it annihilates this thing, which is at most K. Again, this is non-negative, but I can then drop it. It becomes only more true. And I get that the Walrasian equilibrium price on J is bounded below by this term, minus this term. Which should look familiar. Right, so this is the VCG price. Right, it's also right there. Okay? So the surplus of the other n minus 1 bidders get when I optimize just for them, minus their surplus share when I optimize for everybody. Okay? So that's the proof. Any questions about that? So again, we're slowly developing more and more connections between the VCG payments and these Walrasian equilibria, which initially seemed like pretty different objects. So now we see that every Walrasian equilibria is at least as big as the VCG payments. Okay. So now, as promised, the VCG outcome is, in fact, a Walrasian equilibrium. Okay, we know it's no bigger than any Walrasian equilibrium. In fact, it is a Walrasian equilibrium. And hence, the smallest such. Okay? So this is the sort of climax of today's lecture. Right? We have a characterization of VCG payments, which just seemed complicated, a difference of matchings. Now we understand that actually they're merely these Walrasian equilibria, which seem like plausible termination points of ascending auctions. And moreover, there's non-uniqueness. You have lots of Walrasian equilibria, but we know exactly which one we're shooting for. It's the one at the bottom. It's the smallest one. Next week, I'll show you ascending auctions can indeed compute that smallest Walrasian equilibrium. Okay. So here's the key lemma. I need to prove this theorem. And this lemma is pretty nice in its own right. It starts showing how VCG payments are nicer than usual in matching problems. Okay? So let MP be the VCG outcome. We've been talking some about matchings when we delete a bidder, I. What I want to talk about now is I want to talk about matchings when I add an extra good. Okay. So let M plus J be the opt matching with a second copy of good J added. So this good is identical in all respects. Okay, so for every bidder K, VKJ and VKJ prime are exactly the same. Okay, so everybody likes it just as much as J. And again, remember we're unit demand. Okay, so everyone only wants one good. In particular, they only want one copy of J. So there's more stuff for sale. We've arranged the space of allocation, so the surplus can only go up by adding a new good J. Okay? And so the claim is, in fact, the VCG payment made for good J is exactly the extent to which the surplus would go up if I added a second copy of J. Okay, so this is the key lemma. So remember, M was our original computation with just one copy of each good. M plus J is recomputing an optimal solution with a second copy of J. This is only bigger, and the claim is that the extent to which this is bigger is exactly the price paid for J. Okay? So this is real. This key lemma. This is special for unit demand valuations for these matching problems. So remember, when we define the VCG mechanism, if you remember in the fall, we defined it super abstractly. We didn't even need a notion of goods, right? All we had were sort of abstract outcomes, okay? So there wasn't even a way to define duplicating a good for the original VCG mechanism. But with the special structure of a matching problem, we can characterize VCG payments in this very simple way. Okay? All right, so questions about that? Otherwise, I'll show how the key lemma implies the theorem, and then I'll sketch a proof of the key lemma. Then we'll be done. All right, this gets pretty slick. So why, assume we prove the key lemma, why would that imply the theorem? Why does that imply that the VCG prices, which we now know are equal to this, are in fact all rise in equilibrium? Okay. All right, so we don't have to worry about goods that go unsold. Okay, by definition, those have price 0. So we're not worried about the second condition of rise in equilibrium. So remember, we're trying to prove VCG's rise in equilibrium. This condition's immediate. So let's think about condition 1. Think about goods that are actually sold. So consider a good that's sold and suppose some bidder I gets it. And we want to prove that this is I's favorite good with respect to the VCG prices. So consider a competitor. Consider some other good L. The lemma says we can understand the VCG price of L, P sub L, as the extra surplus of having a second copy of L. Right, so we have our bidder I. In the VCG outcome M, it's matched to some good J. We have some good L, presumably matched to somebody else. And we're doing a thought experiment where we have a second copy L prime of L. So what I want to do now for you is give you a lower bound on how big this surplus gain is. Okay, a lower bound on P sub L. I want to show you one way that we could make use of this second copy of L to get more surplus. Okay. So here's one, I'm not saying it's an optimal way, I'm just saying it's one way we could use L prime. So we start from just the VCG outcome matching capital M, where there's only one copy of L. Now we say, oh, we're given the second copy of L prime. So let me reassign I to L prime. Okay? So originally, bidder I got good J. Now I have this extra copy of L, L prime. Let's say, well, let's free up good J. We'll give bidder I good L prime instead. Now I'm not going to stop there, because now I've freed up a copy of J. Okay? And now I'm just going to re-optimize from scratch for the other n-1 bidders. Okay? So bidder I definitely gets L prime, and now I optimize for everybody else. What goods were available to everybody else? Well, I've only committed to using L prime, and J's freed up. So there's actually one copy of every single, all of the M goods available, which I'm now going to use optimally for the n-1 bidders other than I. Okay? So start from M, reassign I to L prime, compute the opt matching M minus I of other bidders to the original copies of all goods, which are all currently available. Okay? So remember, P sub L, this is the surplus gain that we get by re-optimizing with an extra copy of L. I'm giving you a feasible allocation, so that's a lower bound on the surplus gain you can get. How much more surplus do we get from this reassignment? Well, we gain, okay, so we gain the contribution. We gain whatever values I is for L, L prime L being the same thing. We took J away from I. So we have to account for that. So this is the surplus gain just from this step. And then we get the surplus gain, which is the extent to which re-optimizing from scratch from bidders other than I is higher than their surplus share in the original outcome M. Also known as the VCG payment by bidder I, by definition, which, using the key lemma a second time, is exactly P of J. So let's write this as gain by re-optimizing for bidders other than I. Okay, this is just by definition. This is just what we did. This equals VCG payment of I by the original definition of the VCG payment, which in turn equals P of J by the key lemma. Okay? So the VCG payment by bidder I, right, is the same as the price of the corresponding good that gets J by the key lemma is exactly, well, it is what it is. Okay, it's P of J. So rearranging, what do we get? We get that VI of j minus, sorry, P of j is at least VI of L minus P of L, okay, which verifies the Lavoisian equilibrium condition 1 for the allocation and the prices induced by the VCG outcome. Okay? So that's, again, assuming that we can prove this cool characterization of VCG prices, that they're exactly the surplus increase of an extra copy of the good. Assuming that that's true, then we can conclude that the VCG outcome is a Lavoisian equilibrium, therefore the lowest such. Any questions about that? All right. So final piece of the puzzle then is this key lemma. Okay, so again, suppose I gets good J in VCG outcome MP. Okay. Now we're doing, the whole point of this key lemma is to do a thought experiment where we duplicate this good J. Okay, so I mean, I guess to put it better, consider any good J, consider the winner of it in the VCG outcome I. Now imagine we duplicate good J, we get a J prime. Well, here's the claim, okay? So suppose when you have only one copy of J, and you run the VCG outcome, you do this, allocation procedure. Suppose bidder I winds up getting the good of J. Nobody else gets it. Bidder I is the lucky winner of good J. Now suppose I introduce a second copy of good J, J prime. There's two copies available. Okay? And again, I re-optimize. The claim is that bidder I is still going to be one of the, at most, two bidders that gets a copy of good J. When supply was scarce, when there was only one copy, it was the one that got one. Now there's two copies, everyone values them the same. I is definitely going to get one of those copies. That's the claim. Okay. So I think that's pretty intuitive. Right? So if I gets a copy when it's scarce, it should still get a copy when it's less scarce. It's a little tricky to prove. Okay, so I'm not going to do it now. I put this on the exercise set with ample hints. So claim after adding the duplicate J prime, there is an optimal matching M plus J such that I is still matched to J, or J prime, it doesn't matter. One of the two copies of J. Okay? So I'm going to assume this claim and finish the proof of the key lemma. All right? So, assume this is true. Then, consider this matching that has available these two copies of good J, and consider deleting bidder I. So that takes away one of the two copies of J. So the other n minus 1 bidders, they form a matching, and they don't use both copies of J. They use at most one copy of each of the available goods. Okay, so the matching induced by the other n minus 1 bidders we can think of as a matching with respect to the original good set. So call that induced matching M minus I. With each good used at most once. Okay. Now what I hope is clear is by virtue of this matching m plus j being optimal, max surplus, then certainly m minus I should be the max surplus matching of these other n minus 1 bidders that uses every good at most once. If there was some matching better than m minus I with that same property, well, I would just couple that with matching I to the copy of j, and I would get a better matching than m plus j. Okay, so the most trivial cut and paste argument. Okay? So m minus I must be the optimal such matching. Okay, meaning a matching of the players other than I to using goods at most once. So what does that mean? So that means if we think about the difference in surplus, okay, so if we think about this quantity, the difference in surplus between having an extra copy of j and not. So remember, this is what we want to prove is exactly the VCG payment of j. We want to prove this is exactly P of j. All right, well, in m plus j, using the claim, I is matched to one of the two copies of j. So this is Vij plus the rest of the stuff. And over here, this is also equal to Vij, because again in M, I is matched to j. So that's the whole point, is I gets a copy of the good j in both of these two matchings. Okay, so that part just cancels out. So plus the rest. So the Vij cancels out in the difference. So what are we left with? Well, so this matching is nothing more than I matched to a copy of j, plus the other bidders in this optimal matching m minus I for them. So this is just equal to k not equal to I, v sub k of m minus I. What do we have here? This is just, right, we've deleted bidder I from this sum. That's the part that's canceled out, so we're just left with a surplus share of bidders other than I for the VCG outcome M. Okay. And this, of course, is just the definition of the VCG payment paid by bidder I, and therefore the induced payment for good J. Okay. So that concludes the proof of the key lemma, modulo the claim, that basically by duplicating goods, it's only other people that get the new copies. You don't actually kick people out. So modulo the claim, we have this really nice characterization of the VCG payments. It's just surplus increased by duplicating goods. There's this really slick argument showing that that's enough to conclude that VCG outcomes are all Walrasian equilibria. That simple first welfare theorem-like argument showed that all other Walrasian equilibria are at least as big, so VCG is the smallest. So that's now the line in the sand that we're going to shoot for at the beginning of next lecture. Ascending auctions that terminate guaranteed at the minimum Walrasian equilibria. See you then.